this video, I want to continue our discussion of general planar motion. Now recall that general planar motion is the motion of a rigid body that can be made up of both translation and rotation. It's general, meaning any type of motion. And we want to have a variety of tools available to us to analyze this type of motion. One of those tools that I want to discuss in this video is called instantaneous centers of rotation. And the basic principle behind an instantaneous centers of rotation is that at any given instant in time, if we freeze, the motion, there is a point about which our object can be said to be rotating. So if we can locate where that point is in space, and it doesn't necessarily have to be on the rigid body, it can be kind of any arbitrary location, that gives us the ability to now analyze the motion using our basic fixed axis rotation models. So it's a really useful tool if we can locate where that point is and we can conduct that analysis. So when I say that the body is undergoing general planar motion, just as to recall, what that means is that I have some arbitrary rigid body in this case, and if I look at, say, a point on that rigid body, that point may have some velocity, VA, and it may have some rotation about that point. So these two things can be happening at the same time, right? This point, which I'm labeling A, can be moving with some linear velocity VA, and there can be a rotation of the rigid body about that point. If I want to understand this problem from the perspective of locating its instantaneous center, what I mean by that is that I can take that rigid body and once again represent this velocity VA, and then say that, well, let's approximate, or not even approximate, let's treat this motion as a rigid fixed axis rotation. And for that to be true, the imaginary line between point A and my instantaneous center must be perpendicular to VA. It's just required by the definition of this velocity motion and fixed axis rotation. So using that then, I can say, okay, my instantaneous center must be located along this line, which is perpendicular to the vector VA. But where on that line? That's what we don't necessarily know. However, we do know from fixed axis rotation that the rotation arm, or the distance between the axis and any given tangential velocity component, must be equal to V over omega. So if I plug in VA into this equation and I have omega, because I know the rate at which my object is rotating, then I can locate my instantaneous center, which I'm going to label C, and say that that must be the location if it is R distance away from the vector VA. So that's one way that I can locate and define this instantaneous center. Now let's look at it a slightly different way. Suppose I have another rigid body, looks a little bit like a peanut here, and suppose I know on this rigid body the velocity of this point and let's see, the velocity of, I'm trying to think of something that'll work well. This point is like this. So if I represent these 2 points, let's label them A and B, and the statement that I made up here still holds true, that my instantaneous center must lie on a line that is perpendicular to my linear velocity VA in this first example. Well, that's also true that my instantaneous center must lie on a line that's perpendicular to my velocity VA in this one, on my second example. But it also has to lie on a line that's perpendicular to VB. So in that case, I have two lines that must contain my instantaneous center, and therefore wherever those two lines intersect, I know must be where my instantaneous center is located. So if I go ahead and try to dash in a line perpendicular to VB this way and perpendicular to VA this way, I can locate their intersection point, and I know that that must be my instantaneous center. Great. How about a third way to look at this problem? Because we do run into a scenario where this method, the second method that I showed, won't work, right? And that is if my two velocities are parallel to each other. If these two lines are parallel, such as I'll show here, so if I have a velocity on these 2 points, again VA and VB, then the perpendicular line from each of them will pass straight through these 2 points like this. So it'll be the same line either way. Now, I can't figure out where they intersect, right, because they intersect everywhere. So that doesn't really help me locate my instantaneous center. So what I can do instead in this example is if I draw these velocity vectors proportional to each other, such that their velocities, the length of the vector is proportional to the magnitude and to my geometry, then I can draw a line which connects the head of each vector like this. Pretend I drew that a little better. And then locate where those two lines intersect, and that'll tell me the instantaneous center. Now, the reason this works is because the distance between the center and the velocities, as you can see in this example, increases as I get further away from the center, and that has to be proportional to the distance because I'm getting further away. And by this same equation, V equals R omega, those velocities would be larger as I get further away from the instantaneous center. However, again, for that to work, it's kind of a graphical solution. So for it to work, everything has to be drawn proportionally, and you're making a graphical representation then, and it's not just for show. Let's look at or revisit another example that I talked about before in my last video on general planar motion. And that is if I have a rod connecting two slots, one vertical and one horizontal, and recall that we said that if one of these, if the vertical slot or slider in the slot is moving down, then we know that the horizontal slider must be moving to the right. And this gives me a situation that I can solve just like I might expect, and I can dash in the line perpendicular to the velocity of both of these, and that gives me an easy way to locate that instantaneous center. Again, assuming these lines are perpendicular. What this also does for me is give me the ability to figure out the velocity of any point on this body. So say, for example, I want to know the velocity of a point in the center, of the midpoint of this connecting rod here. Well, I can dash a line back to the instantaneous center, and I know that my velocity must be perpendicular to it. I can relate that velocity to VA or VB by the difference in the distances here, again with that V equals R omega equation. If I want to know the position of this point here, or the velocity of this point over here, I can again dash a line back to the instantaneous center, and draw that in. If I want to know this point, dash a line, draw it in. So I have a lot of ability to kind of analyze any arbitrary location on my rigid body, making use of this concept of locating the instantaneous centers of rotation. Now, one last thing I want to say about this is, okay, and suppose we have our rigid body and we locate the instantaneous center. That instantaneous center moves with time, right? It's called instantaneous for a reason, in that it's only located in that spot at that instant in time, and it's going to move as time changes. So the location of this instantaneous center could travel some complex path. This path is referred to as the space centroid, and it defines the location of the instantaneous center. Similarly, at any point on this path, we can define the curvature of the path and draw a circle there, which shows our radius of curvature of this path, and this curvature circle at that instant is called the body centroid. Now, the body centroid is always tangent to that space centroid. But this gives us kind of a visual tool and tells us little information about how this rigid body is moving through space, how the rotation of it is changing, and therefore the velocities on that rigid body and how they are impacted as it moves through time. All right, thank you.